In this video, we're going to take a look at the concept of isotopes. So what are isotopes? Isotopes are variations of the same element um, with different masses. And the reason they have different masses is because they have different number of neutrons. So since these are variations of the same element, um, isotopes would have the same number of protons, electrons, and also the same location in the periodic table. So what does that mean more simply? So let's take a look at carbon. Carbon is an element. In nature, it can actually exist in different forms. It can exist as a light version of itself, a heavy version of itself, and an in-between version of itself. The light version of carbon is called carbon-12. The heavier version, the heaviest version, is called carbon-14. And the version sort of in between, in terms of mass, is carbon-13. So these are isotopes of carbon. They're all carbon, so that means they have 6 protons, 6 electrons, and they're found in the same location on the periodic table, but their masses are different. And their masses are different because they have different number of neutrons. So these are the isotopes of carbon. Now, if they all have different masses, well, which mass do we put on the periodic table? Remember that we have a square like this, we have carbon, we have the atomic number, and we have a mass over here. So if we look at our periodic table carbon over here, you'll notice that we see a mass of 12.01. So we don't put the mass of just one of these. What we do is we put an average mass there. So in reality, this is an average atomic mass. That's what we should call it. For calculations, we typically round up or down, but on the periodic table, we put the average atomic mass there. Some of you might be doing 12 plus 13 plus 14 divided by 3, and you notice, oh, well, that's not really 12.1, so it's not really the average. It is an average, but it's a weighted average. So we also take into consideration the one of these carbons that makes up the majority. So based on this here, you'll notice that the average is closest to 12. So chances are that the carbon 12 is more abundant. There's more of it compared to the carbon 13 and carbon 14. In fact, we can take a look at this figure over here, and that actually supports what we just said. So here we have standard atomic notations for the different carbons. For carbon 12, and I know that's carbon 12 because of the 12 there, carbon 13, and carbon 14. You can see that they have the same number of protons, or the same atomic number, 6 there, and 6 here as well. And as a result, they'll have the same number of electrons. But again, their masses are going to be different, and that's because of the number of neutrons. To find the number of neutrons, we just do our mass minus our protons. So 12 minus 6, 6 for carbon 12. But for carbon 13, we're doing 13 minus 6, so 7 neutrons for carbon 13. And for carbon 14, 14 minus 6, so 8 neutrons for carbon 14. And I want you to notice that not all of these isotopes are present in the same quantity or the same abundance. You'll notice carbon 12 makes up about 98.9% of the carbon atoms that you would find in a sample. So if I had a handful of carbon atoms, 98.9% of those would be carbon 12. 1.1% roughly would be carbon 13. And then less than 0.0001% would be carbon 14, which makes sense that our average mass would be closer to this carbon 12 mass because there's just more of it going into our average. So isotopes, different versions of the same element, they have to have the same number of protons and electrons. They differ in their mass because their neutrons are different. To represent them, you can simply write the symbol dash and then put the mass that you're dealing with. So carbon 12, carbon 13, carbon 14. If in a question I don't give you a mass, so if I don't say it's carbon 12, carbon 13, carbon 14, just go to the periodic table and just round for calculation purposes. Let's go do some examples. So here we have a few examples where we want to draw some Bohr-Rutherford diagrams, standard atomic notations, and Lewis dot diagrams for some elements. And this time we've specified which isotopes we're looking for specifically. I'm not going to do all these examples, but I'll focus on the first two. And these ones are already done for you in this video, as you've seen on the previous slide, and you'll see on the next slide as well. And then you can try this sulfur one on your own. So here we're given the mass. So we have 2 magnesiums. Let's start with A. We have magnesium 24. So magnesium 24. Let's start off by doing the standard atomic notation. We're just going to do mg. We'll put the mass on top. And the atomic number should be what we see in the periodic table because the atomic number has to stay the same regardless of what isotope you have for magnesium. So let's go take a look at our periodic table to find what the atomic number is. Magnesium, atomic number is 12. So we can put 12 over here. And we can also now figure out the number of protons, electrons, and neutrons for it. So protons would be 12 from the atomic number, electrons would be 12 from the atomic number, and neutrons would be 24 minus 12, which would be 12 neutrons altogether. At the same time, I'm going to do this for magnesium 25. So when we're doing this for magnesium 25, we have the same symbol. Our mass is different, it's 25, but our atomic number is the same, 12. And we can figure out the number of protons, electrons, and neutrons. So protons still 12 because it's still magnesium. Protons is the main identifier for elements. If there's 12 protons, it means you have magnesium because protons are never going to change for a given element. Electrons, because it's a neutral atom, 12 electrons as well. That didn't change. But what's different, you'll see, are my neutrons. For neutrons, I have 25 minus 12, 13. So magnesium 25 is a heavier isotope of magnesium compared to magnesium 24. You would have noticed that in the periodic table, the average mass is 24.31, which is closer to 24. So chances are the magnesium 24 has a higher abundance. There's more of it in a sample than you would have magnesium 25. But we'll see more detail on that later on, how you figure out abundance and percentages given some information. Let's go ahead and do the Lewis dot diagrams. Lewis dot diagrams are not going to change for your isotopes because the number of electrons stays the same and they're in the same location in the periodic table. Magnesium is in group 2, so we know there's 2 valence electrons, and that's our Lewis dot diagrams for the magnesium isotopes. Where you will see a slight difference is, well, as we've seen in the standard atomic notation, but also in the Bohr-Rutherford diagram. So for magnesium 24, let's do the Bohr-Rutherford diagram over here. You'll see the difference in the nucleus, right? We'll have 12 protons, that'll be the same, but the number of neutrons will be 12 here, 12 neutrons. And number of electrons will be the same as for both of them. So we'll have 12 electrons So this is our Bohr-Rutherford diagram for magnesium 24. For magnesium 25, I'm just going to do it over here. Still 12 protons, but our neutrons are different, right? So we have 12 neutrons for magnesium 25, and then electrons after that are the same. And so that answers the questions for magnesium 24 and magnesium 25, which are just different versions of the same element, magnesium. Again, carbon is already done for you on the previous slide, and you'll see another picture on the next slide. And you can try sulfur 32 on your own. As I mentioned before, if there's no number given to you, if I just say, for example, sulfur, then just go to the periodic table, find that average mass, and just round up or down, depending on what's more appropriate, and then you can do your calculations as is. Just be aware of isotopes, as we will see them in more detail in grade 11 as well. Here we can see a figure just comparing the different isotopes of carbon. You'll notice that for the most part, when we look at isotopes, the ones that are abundant in nature are the ones that are stable. There are some that are radioactive, which means they'll break down very easily. So our stable isotopes of carbon are carbon 13 and carbon 12. But regardless of them being stable or radioactive, what I want you to notice is that all these isotopes here have the same number of protons all the time, same atomic number all the time, same number of electrons. But where they differ is their number of neutrons, and as a result, their mass. So carbon 10 has 4 neutrons, 5 for 11, 6 for 12, 7 for 13, 8 for 14, and then that results in different masses. So you have very light carbon over here, very heavy carbon over here, and then in between carbons over here. We're going to do a quick little practice run to make sure you can identify elements based on their Bohr-Rutherford diagrams as a quick refresher. So you can pause the video and try it yourself. So if we look over here, this is just a few ways you can do this. You can say there's 18 protons. So if we have 18 protons, let's go to our periodic table. 18 protons, atomic number 18, that's argon. Another way you could have done this was you could have said, well, there's 1, 2, 3. There's 3 shells, and there's 1, 2, 3, 4, 5, 6, 7, 8, 8 valence electrons. So what that means is you're in period 3, group 18, argon. Proton is the safest way to go because you could always lose electrons or gain electrons. So if you have protons, go with that. If you don't and you're told you can use other information, use the other information that's provided from there. And from here, you can also figure out masses. If you want to figure out the mass, you would simply do 18 plus your 22 to get your overall mass. You'll notice that the mass of argon is 39.95. That's the average mass. This particular picture, if you had to name it based on isotopes, you would say that it's argon 40 because the mass is 40. Here we have 17 protons, so you can pause the video and try it yourself. So if we look at 17 protons, atomic number 17, that's chlorine. You could have also done number of shells and valence electrons. So there's 1, 2, 3 shells, and there's 7 valence electrons. So if there's 3 shells, that means I'm in period 3. 7 valence electrons, that means I'm in group 17. So that would be chlorine. Again, proton is the safest route to go, so go with that. If you had to find the mass, you would once again add the 2 numbers within the nucleus up because they make up the mass. So 17 and 18 to give you 35. On the periodic table, the average atomic mass is 35.45. So if you were asked to write this in the isotope form, you would say Cl 35. And then we get to this element over here. So we have 15 protons. So once again, let's focus on the protons first. So 15 protons means our atomic number is 15. That means phosphorus. So this is phosphorus. And if you want to find the mass, you do 15 plus 16, 31, phosphorus 31. But another way you could have done this if you didn't have the number of protons is to say, well, there's 1, 2, 3 shells, and 1, 2, 3, 4, 5 valence electrons. So 3 shells means you're in period 3, 5 valence electrons, group 15. So that would be phosphorus. Again, safest route to go is your number of protons because that never changes. But if you don't have that, you can go the other routes as I mentioned. So this would be phosphorus 31.